Hello, today I'm gonna do a video on complexity, not just complexity, time complexity. And and for this video, I'll just talk about generalized time complexity and some classification. And in the next video, I'll talk about some detail on those classifications. So, uh, time complexity is basically, uh, the amount of time some machine is gonna take for various output, or how the performance of some machine, some computation machine is going to be affected. Some computer is going to be affected by the size of my input, right? So it's pretty interesting, and it's the most. I think a lot of people think it's the most interesting topic in computer science theory. So when you think about time complexity, with our computers, or basically formally we talk about algorithm, that's because uh, we don't these days we have standardized hardware, right? We have a standardized architecture which is being refined, and we have various class of processors, like from down to atoms and arms to i7s, i5s. They share similar architecture. I mean, Intel ones do share, and but they vary in speed and their cache memory size and performance. So considering I have a computer, given computer, and I'm gonna write some standardized algorithm, then I'll be concerned about how much the time complexity is gonna be, or how much is it gonna suffer from the size of the input, right? You're designing an app, and you really want to know how fast, how fluid your app is gonna work. Uh, so that's when you think about the time complexity of whatever algorithm you're going to use. So uh, time complexity is, yeah, it's difficulty. It's difficulty uh, faced by the computer to handle whatever the input is. Yeah. So here you have your computer, your computational device. Here you have your input. So you have some input of size, and the type of input for now doesn't matter, because based on type it may also uh, make the device suffer, right? Some standardized symbols versus some, so for now it doesn't matter. And the output. So first study, we assume that the algorithm is going to be correct, right? So you want basically you want device, or you want study time complexity for some algorithm that's incorrect. So it's obvious I'm going to assume that my algorithm is going to be correct. So basically my algorithm is going to be correct, and interested in how long it's going to take for me to process a particular string, or some input, some numbers, some alphabet, something. uh, yes. And I'll arrive at an output. So for simplifying it, I'll just say I have some strings, and there could be some problem, that be also part of the string, like uh, how long is it gonna anything, like if these are prime numbers, or if some question and some answer, if this is correct, if they match. So for now I'll focus on decidable problems, that'll always give me yes or no, right? Decision problems, yeah, not decidable. Decidable and non-decidable are different things. Decidable basically means when this program can arrive at a solution, at a decision, right? It's always decidable and undecidable, because it's basic thing. Undecidable means it cannot decide. uh, it may run forever. It may not arrive at a solution, at a correct solution. mm, so my problems are going to be decidable, right? And the output is going to be correct. That's my assumption. If it's incorrect, discard the algorithm, devise another one, or troubleshoot it. uh, and then I'll be concerned about the time complexity, or how long it's going to take. So for studying time complexity, we need some specialized or sometimes some unit. So consider some input of size n on which the computer is going to decide, and you use various algorithms on the same hardware, and you're going to see which one's better, right? Algorithms may have their trade-offs. Some could be faster, some could be some may have high space complexity. That means they may require more memory. So these are trade-off based on technology and based on your requirements. So it's very simple. You have some size, some input of size n, and may your time complexity be some function of n. I'm not worried about other parameters. It could depend on a lot of things, like what sort of input you have. But for now, it's just the size of the input, and that may be something, some function. Yeah, that's Dn. May be something like n. It could be 1. It could be n squared. It could be to the power n. It could be to the power n cube. Various sort of inputs, and interesting ones are like maybe 1 or some constant k, and that'd be like it doesn't depend on the input. It doesn't depend on the input you give it. How small, how big, it won't depend. A problem of the class would be to check whether a computer received an input. You could devise an algorithm that basically does nothing but checks if the computer received an input, right? And if it is it'll give you a prompt that, yeah, I didn't receive any input. Do something. Don't just say. So an algorithm of the class will have to just check the first alphabet in the user inputted, and the had input, and it'll just show, okay, yes, there was an input string. So it won't depend how long it's gonna be, how long or how small. It'll just check the first input, and it'll change its state to yes, there was an input. The othermost classes would be something like n square. These are polynomials, simple polynomials that we've seen in schools. These grow, n grows a little. It's it grows just, it's like directly proportional to how the input grows, the time to process it grows. It could be n square. The time increases faster. It could be something like 2n cube. 2 to the power n or 2 to the power n cube. These increases very, very fast. Something like with some input of 1, the time complexity measure which on some unit could be 2, and for 10 this would go to 1024. Something like this would go to just 100, and for something like I don't know, something like 100, this would go to 10 raised to the power, obviously somewhere about 6, and this would just be what, 10 raised to the power 4, right? So this is like 100 times more, and as I increase, my gap's going to increase, right? So this is very enormous. So basically what we're doing here is we're studying how it grows, how the time complexity grows as I change my input. So because we're only concerned about growing, so we could take asymptotes. Asymptotes are very simple. You have some function, and after some point c here, it is bounded by some standardized function, because it could be some hairy trigonometric blah 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 function you don't want to care about, and this could be a standardized some n square n cube function where it cannot be n square. Some linear function, maybe, I don't know, maybe a kn, and after some point c, it bounds it. By that I mean it's greater than it. So that's because it grows faster than this function does, right? So we've devised, we have assigned something called the big O notation. That's nothing but if this is something k to the power, k times n, k times some function, and this is gn, some function of n, this is some function of n again, n is the input. Then simple big O notation is just defined that the big O notation of gn, some function of n, is going to be O of fn, some function of n, right? So this gives me, I don't want to care about some hairy little function, a huge function something I cannot really process, but this could be a very simple function. And this gives me an idea of how this function grows. So this is a standardized notation called the Pico notation. And of course, this gives us a great idea of how it grows, right? So in the next video, I'll be talking about the various classes of complexity and give you a brief introduction.